7K. We're going to talk about RAID RDP or RAID DP, diagonal parity or row diagonal parity, because there's row-wise parity and there's diagonal parity. And this is a very tightly tied to RAID 4 algorithm. So let's get myself back to the right screen here. Okay, so in our course outline, we are talking about complex data protection, diagonal parity RAID. This is not Reed-Solomon coding. That is another way to get multiple redundant protection. We'll get into that. That's actually got 2 lectures assigned to it because it's a complicated enough subject. Or maybe it's not complicated and I just think it is. You can tell me if you think it's not as hard as I think it is. I'll just throw one of the lectures away. Okay, so things to note for next semester. Sorry, you're stuck with it. Disk blocks are a fixed size, usually 512 bytes historically, back in when they first invented disk drives, right? Or around in the 2010 range, they started making disks that had fixed sector size of 4096 bytes or 4 kilobytes. And I'm not paying attention for the last few years. Maybe someone's out there making even bigger ones. This is a convenient size. You got a lot of small files, you know, Word documents that aren't going to be huge. Well, although they put enough junk in Word, maybe the minimum size is over 4 kilobytes now. I don't know. Type in a 1 character Word document. Maybe it takes up 4K on your space because it's got all the metadata, right? In any case, A1, A2, A3, A4, AP going across, that is called a stripe. So there are 4 stripes colored here. Within each disk, the piece of the stripe that is on that disk is called the segment. So A1 is a segment, B2 is a segment. Each of these different colors on different drives is a segment. Now the segment size on a volume is configurable, right? You can use the standard block size on the drive, 4 kilobytes, half kilobyte. You can use 64 kilobytes, so it's got a huge chunk of sequential data. It'll write 64 kilobytes worth of data here, and then it'll write 64 kilobytes here and 64 kilobytes here, calculate the parity based on that, right? If you do an I/O smaller than, what was it, 172 kilobytes, in that case, you have to do a partial stripe right? So, you know, this sum total, the stripe size is the number of data drives multiplied by the segment size. 8 kilobytes, 256. Your best segment size for your application maximizes the number of I/O operations that are single segment full stripe I/Os. So, you know, if you've got a company out there making movies, right, and they've got each frame on their DreamWorks does this. Pixar used to do this. Use the NetApp data storage product, right? And so they'll configure their array so that they've got huge segment sizes. So each segment is basically 1 frame in the movie, because those are really data intensive. You know, the amount of digitized data in a movie when you turn it into a digital image is really big, right? On the other hand, if you're storing, you know, text files, right, then you're going to use a lot smaller segment size because you don't want to be out there reading 64K worth of data in order to retrieve a 1 kilobyte file, right? And if you update that file, you definitely don't want to go out there and read 64 kilobytes from the data drive and 64 kilobytes from the parity drive and then add them together and then rewrite another 128 kilobytes back out for 1 kilobyte worth of update, right? Okay, so we got an example that we're going to use in this class. We're going to start with a RAID 4 example. Block size is 1 byte. Or really the block size is 64 bits. It's an integer. I'm just going to make a table of integer values, but I'm going to limit the size of the data to just a single byte. So the segment size therefore is 1 byte. What is the stripe size? In this diagram here, I've got data 0, 1, 2, 3, 4, 5. the stripe size is 5. Okay, 1, 2, 3, 4, 5 data drives. So 5 bytes or 5 integers, as it were. In this example, we're not going to do anything fancy about maintaining state of the drives or anything. We're just going to say if we want to fail a drive, we just mark it, shove it all to zeros. We don't have any error checking in this example. I put some in the RAID DP example that we show next. So reminder, now to go to RAID. Well, let's go look at the code first. First thing I have to do is find my Chrome here. That's rather interesting. There's supposed to be another file in there. Hopefully it'll show up soon. Otherwise, I'll go looking elsewhere for it because I have extra copies. So what does this code look like? Well, we start off with Python code to dump the drives. This is basically to just show all the data that's in our little play volume that we're making, right? We can actually run that. And then, you notice here we got the doc string. The importance of doc strings, if I look at the underscore doc file, or if I just type dump drives question mark, it'll tell me that this is a function. This is like, tell me information about this symbol. So it tells me that symbol is a function, and here's the doc string for it, and this is where it's located, so on and so forth. All right, so now we need some helper functions. We need to be able to generate that p parity, right? So how do we do that? Given our number of drives and the size of each drive, number of blocks in each drive, we're going to go down there and say for B in the range of all the blocks, for D in the range of all the drives, we're going to say, first of all, we're going to initialize that parity drive. Python -1 index means the last one. So we're going to have data parity is going to be the last drive in the list. And then for each of the data drives that's out there, again, the number of data drives is 1 less than the total number of drives. We're going to take the data on that drive. We're going to XOR it on the drive there, drive DB. We're going to XOR it in with the data that's on drive -1 at that block, and then put it back out there, right? And we got a little quick and dirty debug print statement to just show what's going on. So we can run that code to compile it in there, or pull it into bytecode, Python bytecode, and then we can interpret it later. We go out there, we say we're going to import random numbers. We're going to say 6 drives, 6 blocks, pick a random seed, initialize all the data drives to zeros. So for each drive is 0, and then each block on every drive is 0. And now we're going to seed it with a pattern of integers. And we're just going to make some random numbers, 0 to 15. We're going to print it out in hexadecimal. And so the values we get are going to be here, C, 7, 3, 8, so on and so forth. You notice the P drive, we didn't put anything on it yet, right? So now we're going to go ahead and generate the P parity. And we can see here is we see as we're generating P parity, we start with C, which is 12. We XOR a C in. That makes it go to 0. We XOR into 7. We now have 7. We XOR a 3 with the 7. We get 4. We XOR an 8 with the 4. We get back to a C. And so each of these things is calculated just by XORing all these together. And basically what we're saying is every bit on here is set so that that particular bit on this stripe has a parity of 0. All right. So C, the 8-bit is on, the 8-bit is on, the 8-bit is on here, it's off here, it's on here, it's on here. 1, 2, I'm sorry, the 8-bit is not on here. 1, 2, 3, 4 bits have the 8-bit on of the bytes, okay? We're define a function to rebuild the drive using the XOR parity of all the other drives. So basically what we're going to say is we got some drive, we've zeroed it out. We take all the drives, we XOR the data back onto that drive that we specified there. So the drive to repair is our new value, right? So we're just going to XOR everything onto our drive to repair. and we're not initializing it or anything like that. So we're going to fail drive 2. So we've seen that where we had data on there before, now it's zeroed. And we call it rebuild drive. Just for grins, if you want to see this, we can turn on the debugger, view the debugger panel over here. And we can see as we run this line of code here to rebuild the drive, it'll actually drop into that code. We can see we're on block 0, drive 5, step over that, and it will print out eventually the statement. Actually, it'll go back around to the loop. We can actually watch it in the debugger, go through the loop one line at a time, see the variables as they're changing. We're now on block 0. We're looking at drive 1. We're on block 0, drive 1, block 1, drive 2, block 1, drive 3, so on and so forth. We eventually get through all the drives at block 1, and we go to block 2, right? So debugger is great for watching what's happening. You don't have to have extra print statements in there. It'll run and do whatever you need to. Okay, we're going to turn the debugger off. And let's close the debugger panel there. Okay, so now we've rebuilt drive 2 down here. Because there's no error checking in this code, we can be silly and fail the drive by rebuilding it. In other words, the parity is 0, so if you try to rebuild a drive with the data already on it, it's going to end up changing that drive to zeros. And we could corrupt the data by rebuilding with a failed drive, and so we can mess up the data on some other drive. And what we see here is that if we do this, we've actually swapped the data onto a different drive. So where we had a 7 on drive 2 before, and this is just silliness, we got the 7 on drive 1. So the data is actually still there because we cleaned it out. It's just moved around in the wrong order. If we actually read this data, we'll get messed up data because all this data will be scrambled. So this is not a great example. Don't use this as the basis for a product. So don't try to steal this, run out the door, say I'm going to sell a RAID system now. No one's going to do that. This is my code. Yeah. Okay. No one wants my code. Again, our RAID DP stripes. There's 2 kinds of stripes. There's a RAID 4 stripe. In this case, we've got a 4 + 1 RAID 4. And on top of that, we layer a 6th drive, the diagonal parity drive. The RAID 4 stripe is simple XOR calculations. So if we were actually doing this with XOR, we'd say 3 XOR 1, XOR 2, XOR 3, which would be a result of 3. So we're doing it with XOR calculations. We start XORing these down here. This would turn into 6 is the XOR. And if you want to understand that quickly, you could say 2 and 2 cancel each other out when you're XORing. 7 and 1, 7 is 1, 1, 1. And then the 1 turns off that bottom bit, so you get 1, 1, 0, which is 6. So the actual XOR calculation should be 6. But you can see there's a diagonal stripe on there, right? So the question is, how do we form these stripes? Well, we start with what we call an extent. The layout of the stripes is basically arbitrary. They have to be diagonal, but the order of stripe 0, stripe 1, stripe 2, where they start and so on is basically up to the developer who's coding the system. When NetApp did RAID DP, they did it this way. When they went to RAID RTP, which is basically RAID triple parity, which has got stripes going in opposite directions, they use different values just to confuse people, or because the developer was a curmudgeon and wanted to do it their way. National Curmudgeon Day was a few days ago. Yeah. So, so in this case, this is drive 0, drive 1, 2, 3, and the parity drive. This is diagonal stripe 0 in purple, diagonal stripe 1 in blue, 2 in orange, and 3 in red. There is no diagonal stripe 4. I'll let you think about why for a minute, and I'll come back and ask you in a little while Why is there no diagonal stripe 4 when I've got, 4 data drives, right? So our diagonal stripe is you just take the drive and the block, you subtract the block from the drive, and that tells you what diagonal stripe it's in. Drive 1, block 0 is in stripe 1. Drive 3, block 0, 1, 2, right? 3 minus 2, that's also in stripe 1. Drive 3, block 1, 3 minus 1 is in 2. The orange stripe is diagonal stripe 2, right? So simple calculation, if I say, I got this layout of this volume, what stripe is this block in? You just do the math. Now, it's important to recognize that that is a modular calculation. In other words, if you're down here, it's not stripe 0 minus 0, 1, 2, 3. It's not stripe negative 3, right? This is, in fact, stripe 2, because we're doing the calculation modulo 5 because there are 5 drives in there. So minus 3, you add 5 to it, you get 2. The block on the diagonal parity is equal to the diagonal stripe number. And this is a layout. And all this does is it gives us stripes that start here and they go 1, 2, 3 horizontally across on the data and parity drive, and straight down 0, 1, 2, 3 on the diagonal parity drive. We're going to use that as our convention in this class. So here, we failed 2 drives, drive 0, drive 1, right? So how do we rebuild the data? Well, we already started in this slide here from the marketing people. They said 12 minus the data on these drives. And again, XOR, subtracting, and addition are the same thing. So we'd actually have over here a 6. We'd XOR the 7. We'd XOR 2s. That would do anything. We'd XOR, and we get a 1 as the result. 6 XOR 7 is going to be 1. 12 minus 7 minus 2 minus 2 is equal to 1. So we know that data on that drive is a 1 at that particular block. Now, drive 0 and drive 1 are failed. It means every RAID 4 stripe is dead. If this were a RAID 4 volume, there were not that DP drive in there, you would not be able to read any data off this thing, because you start to go out there and you find these holes in your data, right? You couldn't figure out what was supposed to be at that block there or there. But because we have diagonal parity, we can have some of our diagonal stripes here. Okay, diagonal stripe 0, the purple one, has 2 dead pieces. Diagonal stripe 1, the blue one, has only 1 dead piece, and we've already rebuilt it. We can rebuild drive 1 S0, right? Diagonal stripe 2 has only 1 piece with a hole in it. That's on 0. So we can rebuild diagonal stripe 2. Diagonal stripe 3. We see we have 2 holes in there, right? So we can't rebuild diagonal stripe 3 because it's got 2 missing pieces. So we have to chain our way through the rebuild. We have to start with diagonal stripe 1 and diagonal stripe 2. So we rebuilt that one first. And then we can rebuild drive 0, block 3 from diagonal stripe 2, the orange one. Now that we've done that, this particular portion of the volume is now degraded and not dead. So we can use horizontal parity, and we'll put the green circle on there to indicate we're using horizontal. I should have probably picked a color that started with the letter H and a color started with the letter D, but I didn't. I picked red and green. So we can see once we have this rebuilt, we can rebuild this one. Once we have this one rebuilt, we can rebuild this one. Now we can chain that forward, because now suddenly this diagonal stripe 0 is no longer dead, right? Diagonal stripe 4 is no longer dead. So you can rebuild drive 0, 2 from diagonal stripe 3. And we can rebuild drive 1, block 1 from diagonal stripe 0. Again, drive 1, block 1, 1 minus 1 is 0. So this is stripe 0. We've done that. Now we've got another horizontal parity we can rebuild, the diagonal parity. So the rebuild process in array DP is, you find the place where you can start. And sometimes there are 2, and sometimes there's only 1. And you just keep rebuilding using a diagonal then a horizontal, and then a diagonal, and then a horizontal. And you can do this kind of zigzag. You're stitching it back together, one block at a time, or one segment at a time, 64K segments perhaps, right? So you stitch the volume back together over a process. When we get into the RAID 6 PQ, Reed-Solomon coding, we'll see that you're actually using just a single math calculation. Boom, there's the data, right? So there's different advantages and disadvantages. We're going to do a simple example here. Did you bring markers? What? Yeah, dry erase markers. Okay. We might do an example on the board if we have time after this, but I want to make sure I get through this. This is the simplest possible RAID DP volume. It's got 2 data drives. So how many diagonal stripes does it have then? It has exactly the same number of diagonal stripes as our data drives. 2 drives, 2 stripes, right? Which blocks are failed though? Well, drive 0, block 0, and drive 0, block 1, block 2, and block 3, obviously, because drive 0 is dead. And also parity drive block 0 and parity drive blocks 1, 2, and 3, right? So if we look at this from a block level or a byte level from our RAID 4 example, or looking at it from a segment level from an actual storage subsystem perspective, right? We can see that we have a problem of rebuilding 8 chunks of data in this case, right? What can we reconstruct? So what diagonal stripes are these drives part of? Okay, so who can tell me what diagonal stripe this is in? Drive 0, block 0. Drive number minus block number tells you what the diagonal stripe is. That's diagonal stripe. 0. 0 minus 0 is 1. 0, right? And what diagonal stripe is this in? 0. 1 minus 1, right? And what diagonal stripe is this in? This is the diagonal parity drive. It's at offset 0. So it's diagonal stripe 0. Offset 1 is in diagonal stripe 1. Offset 2, what diagonal stripe is that in? Well, the diagonal stripe only has 2 drives, so it only goes from here to here and here to here. Let's go ahead and see. There are only 2 diagonal stripes in here. There's diagonal stripe 0, and that's it. 0 minus 0 is 0, 1 minus 1 is 0, and then block 0. And the other diagonal stripe is diagonal stripe 1. 1 minus 0, 2 minus 1, and block 2. Well, what are these? Well, that is another extent. So each diagonal stripe wraps its way all around, and then we start over with another extent. So this is, in fact, extent 0, extent 1, extent 2. We count these sequentially, 0, 1, 2, 3. We count these by extents. It's extent 0, block 0, extent 0, block 1, extent 1, block 0, extent 1, block 1, so on and so forth, right? So it just keeps repeating. If we have 10 drives, it would be extent 0, block 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that would repeat 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, extent 1, and so on and so forth, right? So it's a strictly repeating deterministic pattern. We're not doing any kind of randomization, locating of the data on here, right? When we talked about dynamic disk pools, we saw we were randomly locating the data on the drive. Well, you can do that on top of this algorithm. You make this algorithm think it's using fixed locations, fixed calculations, but then you can, underneath it, you can do whatever you want to and just confuse it, right? It doesn't care. So here we got, what can we rebuild, right? Well, we can start with diagonal stripe 0. We can't rebuild off the P parity because there's 2 dead pieces out of the 3, right? So that RAID 4 volume is dead. So we have to rebuild from diagonal. So we can start here. That's in diagonal stripe 1. And we can also rebuild in extent 1, right? And then we'll go on and we'll say, let's rebuild from there using the horizontal stripe, right? So we'll rebuild this one next. Second step, P0 and P2, okay? And then we're going to, so we stitched our way forward. Now we're going to rebuild diagonal stripe 1. So we can start here because this is not part of any diagonal stripe, right? That's a horizontal stripe. So we're going to rebuild that as 3, third step, and then the fourth step is to use the RAID 4 and copy back to diagonals drive 0 block 1 and drive 0 block 3. So we've successfully rebuilt it. So here, what are the values that we're going to rebuild? Well, we're going to start by rebuilding here, right? So we're going to take 6 and A, we're going to XOR those together, we're going to get C. We're going to plug in a C there. Now we're going to take C, I'm sorry, this C, XOR 7 is going to be a B. We'll fill that in there. Now we go crosswise. C XOR 3 is F, B XOR 9 is 2. Fill those in there. Next step, we're going to rebuild on the P parity. And again, from this previous slide, you can see we did this. Step number 3, we rebuild here, and then we go backwards the other direction to rebuild at step 4. So we've got step 1, step 2, step 3, we're going to fill this in. 3 XOR 2 and 9 XOR 5. Goes there, and then 6 XOR 1 and C XOR C give us 7 and 0. So we've successfully rebuilt those drives in this simplest of all, well, not simplest possible, because we could have only had one extent, right? But this is basically the almost the simplest possible RAID DP volume you could create. As we add more data drives in there, we start seeing our reconstruct go in different, go more complicated. And we'll go ahead and do that on the whiteboard, assuming I can get, no, there's no point doing that. Well, we'll do that for the people in class, and then hopefully we'll be able to record it tomorrow when we have a podium computer working. Okay, so limitations of RAID diagonal parity. Your diagonal stripes constrain the volume size. If there are n data drives, every diagonal extent must contain n segments of the data, right? So if I have 6 data drives, how many segments do I have to have per diagonal stripe? 6. It is obvious, right? So the simple solution, if a customer says, I want to make a volume with 8 data drives, and I want it to have 15 blocks, we'll either just say, I'm sorry, you can either make 8 or 16, or we'll just say, okay, fine, we gave you a 15 drive one. We'll just bump it up to 16 internally and pretend you made a 15 block long volume, right? The diagonal stripes also constrain the number of drives in the volume. That RAID diagonal parity is considered an extra diagonal parity on top of a RAID 4. And if you start failing the right combinations of drives, you get into modular arithmetic problems. So the size of that RAID 4 volume must be a prime number. You can have a RAID 4 volume with 3 drives, which is what we did before. You could theoretically have one with 1 drive, which is basically a RAID 1, right? You could have 5 drives, 7 drives, so on, but you cannot have a 9 drive wide RAID DP, because that would be an 8 drive wide RAID 4 underlying it, and 8 is not a prime number, right? So there are certain combinations of drive failures that you're not able to recover. Your simple solution to that, we'll say, is dummy drives, right? So back to this question here. See these white colors on here? There is no diagonal stripe 4. Why is there not a diagonal stripe 4? You thought about it? You got the answer? I'm going to see if anybody can give me the answer for why there is no. I've got 4 data drives, my diagonal stripes, so therefore I have 4 diagonal stripes, 0, 1, 2, 3. I could, if I didn't want to worry about that whole problem with the parity and the prime numbers and stuff like that, if I just made one more stripe right here and protected it with diagonal parity, I wouldn't have to worry about this whole prime number of drives. But why don't we do that? Any guesses? The answer is, where does the diagonal parity for that go? If the diagonal parity for stripe 0 is at block 0, and for stripe 1 is at block 1, and stripe 2 is at block 2, stripe 3 is at block 1, and obviously the diagonal parity for stripe 4 has to be at 4, right? So now we have 4 data blocks on drive 0, 4 on drive 1, 4 here, 4 here, and 5 data blocks or 5 segments on the diagonal parity drive, right? And then we go to our next extent, and all our calculations are wrong, right? So in order to keep the drives, the ability to have the drives the same name and not let the math get all complicated, they said we're not going to store the data on this last diagonal stripe. Time 1:10. Good, excellent. Let's go look at our sample now. Let's see if we have our sample code yet. No. This is relatively annoying. Tell you, I was working on this last night, and that file was copied to this directory yesterday. I looked at it, but recopy it. All right, here we go. This is a demonstration of the RAID DP algorithm, and it gets a lot more complicated than the RAID 4. So we'll see a lot more coding here, but it's posted on Blackboard. I hope it's posted on Blackboard. I'll go look anyhow. And you can download this afterwards. And we're going to do some work on this. We're going to have an assignment, is my plan, where you're going to go out there and try to finish this code, because this code doesn't reconstruct yet from a double drive failure. Here's our dumping the drives. We put out a little pretty header where we say, you know, the drive number, the parity drive, and the diagonal parity drive. And then we print out the data on the drives. In this particular printout, we're using hexadecimal. If you prefer to make it decimal, you can just go out there and change this to, you know, O3D or whatever you want to, and see it in decimal. So when you download this code, you can mess it up however you want to, right? We go out there and we, yeah, okay, that's a, and what this notebook does is it defines a few helper functions, creates a zero-filled RAID DP volume with a specified size, initializes the data drives with a pattern that you specify, or one of 3 different patterns. Then it initializes the P and the DP parity drives using the data drives. It does not contain the code to fail and rebuild drives. I mean, it has the code to fail and rebuild a single drive, because that's inherent in the RAID 4, already was there, and inherent how to create the diagonal and horizontal parity in the first place, right? So it can handle single drive failure, but to handle the double drive failure, it's not there yet. So, mwahaha, you will laugh. You get to code that in there as an assignment. So we're going to dump the drives. Boom. What is the signature of the dumping the drives? Now we've got the random number. We're going to go ahead and have a function called initialize data drives. We'll import random. We'll initialize these to zeros, just like we did in the RAID 4 algorithm. Then we have a powers method, an increment method, and a randomize method. So random is just put random numbers in there, small random numbers. Powers is the first drive has ones. The second drive has 2. The second drive has, oh wait, 2 to the 0. Yes, 2 to the 2. 1, 2, 4, 8, 16. We just double the data on the drives. And increment is we actually add the drive plus the byte offset into the value. So we have different ways you can play with the data, look at what it looks like, see how the XORs work when you run it yourself on your own time. Now we're going to have a function called generate the P. And then this is exactly very similar to what's in the RAID 4 algorithm, generate P, except, we have to make sure that we subtract 2 from our drive so we don't try to initialize the diagonal parity. We want to initialize the second to the last drive. We want to use the first, n-2 drives, not the first n-1 drives. So this number has just been adjusted. Simple, straightforward coding. I didn't think about this too hard. I didn't run this through ChatGPT. I probably would have got better code. Anyhow, so we initialized the P parity. There's a print statement. It's in there. It's commented out. It's to show it building it. Now generate the DP. Now here we're going to go out there. We're going to say, so first question is, how many blocks do we have? How many drives do we have? Our extent size is the number of data drives. There's a P parity and a DP parity, so the number of data drives is 2 less than the number of drives. Therefore, a number of extents must be a multiple of that. And if it's not an integer, then there's an error. Let me go back and fix it. Now, for each extent, I'm going to repeat over and over for every extent in our volume. We're going to go for every diagonal stripe from 0 to the number of data blocks, data drives we have. We're going to figure out the first data block, or figure out where the data block is in the diagonal parity drive. Extent times extent size plus diag stripe. Okay, so extent 0 is going to be diagonal stripe block 0. Extent 1, it's going to start over whatever size the extent it's going to say is that. It's again, it's DP block 0. We're going to initialize the data on that block to 0. Whatever was there before, we're just going to clean it out because we're initializing the data. We're generating fresh data on there. If there was something there before, we're going to just ignore it, right? We could just write over it, but this is I don't know why that's in there. So our drive number starts with our diagonal stripe, starts with that topmost drive, right? Block 0, drive whatever, that's going to be the stripe. And then for the offset in the size of that extent, we're going to calculate the diagonal block is the offset based on the extent size. And so we're basically going to count through for each diagonal stripe. We're going to count through to the next block and drive in that data. So now we say the diagonal parity block on the diagonal parity drive is XORed with the drives at drive numbers and the diagonal block associated with this diagonal stripe. And then we go to the next drive. And if the drive number hits our modulus, which is the size of the RAID 4 volume, including the P parity, we'll wrap it back around. Okay, after we pass the P drive, then the drive number would give us a calculation. It's a negative number. We just calculate that modulus and it'll get us back into the positive range. So we'll go ahead and as soon as we wrap around that past the P drive, we'll get everything is correct. Cool. You're probably not with me at this because it's boring reading someone else's code, right? But you can play with it. So let's go ahead and try to initialize this. Let's try this here. We'll say we got 7 drives. Is that a valid size for a RAID DP volume? 7 drives means there's an underlying RAID 4 with 6 drives. That is not a valid size. I'm not checking that in this code, right? It doesn't matter. We're not rebuilding yet anyhow. But when you go to do a rebuild, if you don't check that, you might find problems with the rebuild. So if we try to run this code now, everything looks fine. We got 7 drives, 7 blocks. We initialize 1, 2, 3, 4, 5, 6, 7. I tell it to use the powers method. So first drive is all 1s, second drive is all 2s. The cool thing about that is when we generate the P, parity, it just adds them all up. 1, 2, 4, 8, and 10 makes 1F. Now we're going to generate the DP, and we're going to get, there we go, there's our error. Generate, we get a value error. The number of blocks is not a multiple of the number of data drives. So since the number of data drives is 5, we have to make this a multiple. So let's make that 15, shall we? And run the code. And now we got our data blocks. We can use a different initialization method. And again, this is drive 0, block 0, drive 0, block 1, 2, 3, 4, 5, and so on. And we get outside of our range of 1 to 15 pretty quickly. Now we can generate the p parity. And you can see this is, we just summed all these together. 1 plus 2 plus 3 plus 4 is going to add up to 4. 1, 2, 3, 4, 5 is going to add up to 1, and so on and so forth. So we've initialized all that. And now we can run our generate DP. And again, it's taken this, 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 and this. 1, 2, 3, 4, 1, 2, 4, 6, 8, and 5. That's diagonal stripe 0. We XOR those together, and we get an 8. Diagonal stripe 1, we do it 1, 3, 5, 7. I'm sorry, 0, 2, 4, 6, and 8. And that's the end of the stripe. Stripe 1, 1, 3, 5, 7, and 8. XORs to 8. 2, 4, 6, 3, and 4. We XOR those together, and we plop that into the third position, and so on. It's initialized the whole thing. Now, we have code in there to rebuild a RAID 4 drive. And we can go out there and say, and define a rebuild drive. So we say, well, ignore that. Yeah, okay. We can't do a RDP rebuild. That's a stub function. You'll have to figure that out yourself. If we fail drive 2, here it's all zeros there now, right? Now to rebuild drive 2 from RAID 4, we can just say, got to run the code. R4 rebuild drive, and there we've refilled in the data that was on drive 2. Okay. We can also fail the P drive, and rebuilding it by saying rebuild drive on the P drive, and the P drive number, and we're using the number of the P drive, and that will work. Or we could just rebuild the P drive by just saying generate the P parity again, call that function we initialized in the first place, and it'll rebuild it that way. If we fail the Q drive, we don't have the R4 algorithm. You can't do a rebuild algorithm on this. So if we try to fail the diagonal parity drive here, and we try to rebuild it using the R4 rebuild drive, we don't get anything. Oops. Yeah, so we run that, we get zeros. We still have zeros. It doesn't succeed in doing anything. But if we rebuild the generate DP, we can rebuild that diagonal parity drive. Okay. Yeah, time is good. So now, how would you go about rebuilding from a double drive failure? So start thinking about that, right? And again, in the lecture, we started with an example where we had to figure out what the diagonal stripes were. We had to figure out what diagonal stripe we could start rebuilding with, and then work our way through it. And of course, we can go in there and change these size parameters as much as you want to. Just go back up here and say, if I use 6, and then this has to be a multiple of 4, we can now initialize it, fill it in, fail drive 2, rebuild it, and we'll see the 0, 1, 2, 3, 4 drives out there. Play around with that, see how the different algorithms work. Do I put these up at? I guess I have to turn off the. No. Yeah, I want to write on the whiteboards. Oh, I know I can do this. What do you do when you play them? Yeah, cool. Okay. Let's turn this off. There. So let's define array DP with 4 data drives, 1 parity, and 1 diagonal parity. Okay. And we'll draw this as a table. And we'll do a single extent. Okay. So I got 1, 2, 3, 4, 5, and 6. Drive 0, drive 1, drive 2, drive 3, parity, and diagonal parity. Okay. How many blocks are there going to be in my extent? 1, 2, 3, 4, right? So there's going to be 4 blocks or 4 segments. Okay. So this is going to be 0, 1, 2, and 3, right? Now, I'm going to move this thing around. When I move the marker over something that's in diagonal stripe 2, say, got it. Okay. So I'm just going to start randomly moving around here. Okay. Am I in diagonal stripe 2 yet? Where does diagonal stripe 2 start? Huh? This one here is diagonal stripe 2. Where else is in diagonal stripe 2? 3 minus 1 and 4 minus 1. Okay. And where's the last one? Tell me where it goes, up or down? Right? Okay, so now yell out when I hit the right block for diagonal stripe 2 on the diagonal parity drive. Here, 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 yep. Again, block 2, right? Okay. And so likewise, 0, 0, 0, 0, and 0, right? And 1, 1, 1, 1, and 1. 3, 3, 3, 3, and 3, right? And this is not, we'll call it F, okay? That is final. F for final. That's the final block we have to rebuild. We can only rebuild these blocks here off the horizontal parity. Okay. Okay, so this is the data we have on our volume now. So let's fail a drive. What drive should I fail first? Well, remember, that was 3210, right? Okay, what other drive should we fail? 1? You don't want to fail the diagonal parity drive? Okay. 1, 0. Now, did I fill this data in by calculating the parity correctly? I did not, right? I just put in random numbers. So am I going to rebuild the same data on those drives as I just erased? No, I'm going to rebuild the data that would have been there if I'd have calculated the parity correctly. In other words, what I'm supposed to do is start by filling in these first 3 drives, and then I calculate this 0, XOR 1, XOR 2, XOR 3 turns into a 0, right? I would have initialized this all right, right? So we're going to have little mystery game. We don't know what data we're going to rebuild, but we're going to rebuild the data. So where can we start? What drive is diagonal stripe? Diagonal stripe 0 is dead, right? I'll mark that as dead. And there's our 2 diagonal stripes. Diagonal stripe 1. Dead. Diagonal stripe 2. We've got, that's degraded, right? Because there's only one piece in diagonal stripe 2. We got 1, 2, 3, 4, 2 still left, right? Diagonal stripe 3 starts here. 1, 2, 3. There's only 3 pieces. It also is dead, right? Well, this looks alarming. We've only got one possible place we can start our rebuild from, right? Okay, well, let's do it. Diagonal stripe 2. Diagonal stripe through, we can rebuild this one right here. Okay, so we're going to do our XORs. 2, XOR 2, XOR 2, XOR 2 gives us a 0. Okay, now we can use horizontal stripe 1, right? The RAID 4, and we can rebuild this one here. What's the value that goes in here? F XOR 1, XOR 3. F XOR 1, XOR 3, right? Which turns out to be D. We want to do the math? Yeah. If we do the math, it's 1, 1, 1, 1, XOR 0, 0, 0, 1, XOR 0, 0, 1, 1. We add those up, 1, 2, 3, we get a 1. We add those up, 2, we get a 0. Add those up, we get a 1. We add those up, we get a 1. 1, 1, 0, 1 is hexadecimal D. Okay. All right, so I've rebuilt that. Now what can we rebuild? Well, now we see that diagonal stripe 0 is just degraded. So we can rebuild here. Right? So what goes in there? Well, we've got a 0, a D, a 0, and a 0. So that's a D, right? And now we can go off and build horizontal stripe. Rebuild this one, right? So we have 2FD1. F1, 2, and D, right? And we get 1, 0, 0, 0. So the answer here is this should be A1. Okay. Now what can we rebuild? What stripe was that part of? 3. So we can rebuild diagonal stripe 3 is now only degraded. Where's the missing piece in diagonal stripe 3? Right here. Okay. So that piece we're going to rebuild using DS3 is going to be 3, 3. And over here we've got a 3 and a 1. Right? So the XOR the 2 3s, they go away. We get 3 XOR 1 is 2. We're going to plug a 2 in there. And now we rebuild this one here from horizontal stripe 0. 2 XOR 2 is nothing. So this is an F. Finally, we can rebuild diagonal stripe 1. F, 1, 1, 1, and 1, right? Well, 1 and 1 cancel out. I'm sorry, and there's another 1 down here. Sorry. Wait, 0. 1, 1. Yeah. There's only that. Okay. 1, 1, and 1. I believe something's gone funky here, but we'll get it. Okay. So F plus 1 plus 1 plus 1. The 1s cancel out. F and a 1 going to turn into a E. Right. So taking F, we're flipping off the bottom bit. Now we've got horizontal stripe 2, 3, XOR E, XOR 2, XOR 0. We start with E. We flip on, we add a 3 to it, so that flips this bit and this bit. Then we add a 2 to it, that flips this bit, so we end up with F. So this data doesn't look like what we started with, because what we started with wasn't real data. What we started with was just, what stripe is this part of? But this is what the data is supposed to be on there, right? FD, F1, 20ED. We can initialize this with any sort of data, right? And as long as we calculate the parity and then calculate the diagonal parity correctly, we can rebuild any two drives. What do we do if this drive fails? And this drive fails? How do we rebuild the data? We don't rebuild the data. The data is already still there, right? None of the data drives is dead. We rebuild the parity in that case. And how do we rebuild the parity? Same way as we built it in the beginning, right? What happens if I forgot to write the numbers down, F, D, Q, R, whatever the values are there. What happens if this drive and this drive fail? How do we rebuild that data? Can we rebuild, is this horizontal stripe dead? No, it's just a grade. So we just fill in this, 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 and this. Then we recalculate the Q parity, the DP parity, right? So any combination you can take care of. So you can go ahead and build samples in your code. And what I'd like to suggest you do is try building 6 drive wide and 4, 8, whatever, you know, make it small. Start at 4, so 6 by 4, 6 drives, 4 blocks. Initialize to small data, run it, fail it, and then see if you can manually do the rebuild. Run through the algorithm yourself and rebuild the data on there. And then, of course, try it with a 7 drive wide volume and 5 drives, and see which combinations of drives you can fail that you're not able to rebuild. Okay, that's just for fun. You don't have to do that. That's not an assignment yet. The assignment will be for this to code, and I'm debating whether to make this a team project or individual. Might as well get started on the teams, right? So we'll have to form some teams before we get going on that. But the goal then is for you to go out there and figure out how to write the code to be able to rebuild a drive using the RDP. And we actually have to have there's 2 dead drives now, right? So you have to be able to rebuild 2 dead drives using the RAID RDP rebuild function. And it's only in the case where there's 2 drives, not including the DP drive, that you have to worry about that algorithm. So it's not necessarily used all that much. All right. End of that lecture. I have run myself down to the wire. I was supposed to start lecturing on RAID RTP. It is 1:40. We got probably time to do this. Let's go ahead and give it a shot here. This is basically just a quick description of how RAID RTP works. Very short presentation. I'm just going to go ahead and tack this onto the end of the recording we already got. Do I have my cameras and stuff still on? I probably should, yeah, it's whatever. We'll have a bunch of stuff on there that we can't see anyhow. So we're sharing this drive. We'll start at the beginning. RAID RTP. RAID RTP is diagonal parity RAID RDP. So we're still in the same thing. RAID triple parity has N data drives, one RAID 4 parity drive, one diagonal parity drive, and one anti-diagonal parity. So you had another drive out here, right? The anti-diagonal parity. Parity, they went ahead and they rotate the parity, but we're going to use a simple algorithm and assume there's like fixed drives. They actually have marketing materials out here you can read if you want to, and an actual scholarly paper where they describe how the algorithm works. And you can go in there and dig in all you want to and understand it. You have fake missing diagonal stripes. The data in the missing diagonal and anti-diagonal stripes cannot be calculated directly, but you can calculate it indirectly. You start by imagining another block of data on that diagonal parity drive. So we're talking about this missing diagonal stripe that we didn't have any data for. We imagine there's actually a block down here. And we can calculate what would have been here by adding the two crosswise diagonals. So we examine a fake horizontal stripe, the end of each diagonal stripe group. So here's our diagonal parity sets. There's the diagonal. And this is the drop diagonal. If there were room for that, it would be diagonal 0 plus diagonal 1. It would be the sum XOR. If we had that block there, it would actually be the XOR of those data blocks. Because the way we calculated the data, we did a whole bunch of XORing. This actually down here, that missing piece is easy to figure out what it would be if it were there. So we XOR those together, we get that. The anti-diagonal goes the opposite direction. So one diagonal goes up and to the right, the other goes down to the right. And this missing piece would be the XOR of those data blocks. And so when we have a single disk failure is trivial, double disk with both diagonal drives is trivial, two data or one data plus R is trivial. Use the RAID DP, two data or one data plus R. XOR, we use a RAID diagonal parity. Triple disk failure, if they're all parity drives, is trivial. If it's the data in 1R, we use the RAID DP and just rebuild the missing bit. It is when we have a triple data failure where the two data or the R parity, the XOR, the RAID 4 parity, that's where it gets mildly interesting. We calculate the observation that we've got 3 failed drives. This is a fake stripe we can fill in. These are all zeros. These are just the location information on here, right? So the drop block, stripe 6 and so on would be there if there was a missing bit. These are the missing pieces in the horizontal. These are the missing pieces in the diagonal, things we cannot fix. When we add the horizontal and diagonal parity, we see that we have only 4 pieces left. That one cancels out. Okay, so that piece, we make it disappear. And we calculate these 4 tuples for the diagonal and the anti-diagonal parity. Then we can use magic or XOR to sum them together. And that leaves us with the data that was on this drive. It's missing. And I am not going to go into the details of RAID RTP because if you want to do that, you can go work at NetApp. Since one data drive is reconstructed, now you're back to RAID DP reconstruction. You can read the paper if you want to. That's the end of that. Now it's time to do the attendance quiz very quickly, and we'll be done for the day. And I actually have plenty of time. It's just I started late. So I would have plenty of time if I started on time. Okay. Oh, yeah. Sorry, people online. I'm going to stop sharing now. Also, stop recording.